Hello everyone, my name is Xiatian. I am an assistant professor from Xi'an Jiaotong University. The topic of my presentation today is exploring better speculation and data locality in sparse matrix vector multiplication on Intel CPU. Here is the outline of my talk. First, I will introduce the SPM way on Intel CPU. The sparse matrix vector multiplication features the computation between a very sparse matrix and a dense vector, and the result is also a dense vector. In many algorithms, it requires many iterations with the same matrix and multiple different vectors. This gives us the possibility to optimize the structure of A for better performance because the cost of preprocessing will be amortized among the many iterations. We evaluate the SPM way on Intel based on the sparse matrix graph-based matrix selected from the pseudo-sparse matrix collection. We use the Xeon Gold CPU with the Skylake architecture and the latest version of mass kernel library. We do the profiling using the official vTwin profiler from the Intel. And here is the result of the profiling. We can see that the effective execution, which is retiring, is very poor as it only takes 34% of the total execution. And the two major bottlenecks is the bad speculation and the memory access. We can see that this observation is suitable on most graph-based sparse metrics. Then we analyze the bottleneck in details. We can see that in the CSR format computation, there exist two kinds of irregularities. First is that different loops exist among different rows, which means a random branch prediction. Another factor is that different rows require from different vector positions, which means it is hard to get a catch line reuse among different rows. As we know that most modern superscalar CPU relies on the branch prediction to increase the pipeline efficiency. However, a wrong prediction may cause a very serious penalty because it requires the CPU to invalidate the speculatively executed instructions and to recover the CPU state to the branch point. All these actions may undermine the performance. We also know that the branch predictor uses a local and global branch history for the prediction. However, in the case of SPM way, such prediction is impossible because by nature it has no pattern to catch. However, we can see that with the shorter rows, it tends to have a more frequent wrong predictions, and with longer rows, we tend to have a less frequent wrong prediction. This leads us to the conclusion that the speculation penalty is influenced by the non-zero density of each row. For the memory access, we compare two matrices. The web-Google matrix has a bad locality because all the non-zeros are scattering all over its space. On the other hand, the other matrix has a good locality because the non-zeros gathers in the diagonal band. So we can say that the memory locality is influenced by the non-zeros distribution rather than its density. We can measure the graph-based matrix locality using the diagonal band, which measures the proportion of non-zeros in the band as shown in the picture. From the above analysis, we can see that sparse and dense matrix may be bounded from different kinds of performance bounds. To verify this assumption, we divide the matrix into sparse and dense submatrices according to the number of non-zeros of each row. And for each submatrix, we run the SPMV routine and run the bottleneck analysis separately. As we can see in this comparison, the sparse submatrix takes up most of the total runtime, and for the dense submatrix, its major bottleneck is the memory access. For the sparse submatrix, it is bounded by both the memory access and the speculation, where the speculation is the most critical performance bound. Based on the above analysis, we can give the penalty model where we measure the level of memory and speculation penalties according to the structure of matrix. We assume that the less non-zero rows tend to have a higher speculation penalty, and the poorly banded matrix tends to have a higher memory penalty. So then we can assign different optimization goals to different kinds of matrix structures. So to optimize the speculation, we propose the density-based optimization method, which we group together rows with the same length so that the adjacent rows have the similar loop pattern. As we can show that after this optimization, we can have a better speculation, but we also break the original matrix structure and the Y sequence, which may be a problem, which we will discuss later. Then, to optimize the memory access, we propose the bitmap-based optimization. We will segment each row and downscale it to bitmaps according to the picture, and then we put rows of the same bitmap into the buckets. After the buckets are generated, we order the buckets with the gray coding so that the adjacent buckets only have 1 bit difference. In this method, we also consider for the dense rows, where most of the bitmap may be 1. In this case, we use the threshold to select only the more dense sections as shown in this picture. As a result, we have a better memory locality on the poorly banded matrix, but we have no effect on the highly banded matrix because for such kind of matrix, it's better to go with its original structure. Then to consider the problem of DBO, which means it degrades the memory locality as it breaks the original structure. We can combine it with the BBO if the metric is poorly banded. As we can show in this picture, we can use the BBO inside of each DBO group so that the memory access inside each group is improved. We also use a reverse gray ordering among different groups so that the overall memory access is optimized, improved. As a result, for the poorly banded matrix, we can result in both a better speculation and a better memory locality. This leads to the overall optimization scheme. Our scheme follows the principle of the penalty model. We first split the matrix into the sparse submatrix by the number of non-zeros of each row. We already know that the sparse matrix have a higher speculation penalty. The problem is that if it is also suffered from a memory penalty. If the answer is yes, then we only need to optimize the speculation using the DBO method. Otherwise, we use a combination of DBO and BBO to optimize both the speculation and the locality. On the other hand, for the dense matrix, we already know that it is not suffering from the speculation, so we don't care about the branch prediction. We only need to verify if it is bounded by the memory penalty. If the answer is yes, we use the BBO to alleviate this penalty. Otherwise, we don't do anything and just keep it in the original structure. For the evaluations, we evaluate our method on the sparse and dense matrix separately. We can see that for the sparse matrix, only the DBO method has already achieved a considerable speedup. When it is combined with the BBO method, we have a further boost up speedup. Then for the dense matrix, we can see that only the BBO is required to optimize for the memory access, and it has a obvious effect on matrix which is not highly banded. Then we evaluate for the full matrix performance. We choose the baseline to be the original MKL SPMV routine, and we use our method to compare with the official MKL optimization method. And we test it on the 86 graph-based matrices. Here is the evaluation results. On both 1 thread and 8 thread, our performance outperforms the MKL optimization with great margins. And what is more important is that our method helps the MKL optimization to achieve even higher speed up because our method helps a better factorization rate and a better evaluation efficiency. Here is the pre-processing cost of our methods. we can see that our method have an extreme low cost compared with the MKL optimization, which takes like 26 times of the one-shot SPMV execution, when our method only takes 4 times of the SPMV execution. This means our method can be totally ignorable considering the many iterations which is used in the actual algorithm. Thank you.